All right, hi guys. So we are going to do a quick overview of two other wave-related vocabulary words that we haven't really discussed in class, but you did watch or learn about in your previous video, and that's going to be period and frequency. So I would go ahead and on that um, the back of the front page of your packet, that green page. I would go ahead, reference that page. If you have notes on period and frequency, go ahead, read through them really quick. And if you don't, that's a great place to write those so this vocabulary is easily accessible to you later. So, period is essentially the time it takes for one wave to pass. And so when I'm saying like one wave, what I really mean is going from a crest to a crest, or the time from a trough to a trough. And really important that we're looking at the time. Now, frequency is a little bit different. Frequency is the number of wave cycles per second. Okay, so period is really nice. We represent period with a capital T. We represent period with a capital T because P is used for other things in physics, like momentum. And our units are seconds. For frequency, we represent that with like this fancy F. And our units are hertz. Now, hertz is the same thing as 1/seconds, 1 divided by seconds. And really how you calculate your frequency, it's a bit less intuitive than your period, because your period, you're just looking for one wave, but it's essentially your number of waves per unit time, so per 1 second. So if you were to go ahead and work out those units, waves is a unitless number, and then obviously time in seconds. So I want to go ahead and actually look at a graph and see how we can extract this information from a graph. So if you go to page 10, which is one of the pages you'll be working on after you watch this video, and if you go to that bottom half of a page, we see this graph here that looks pretty familiar. It looks very similar to the graphs that we've been looking at, but if we're very careful here, we see that this is a position versus time graph. And so we remember that you cannot, so we can only find wavelength, which is that lambda, with a distance graph. So since this is a distance or position versus time graph, we cannot find wavelength with this time. When we have a position time graph, we can find period and frequency. And frequency. As we are, just like our distance graph, you can find period and frequency from a position time graph. You cannot find it from a distance graph or position graph. You cannot do that. So if we were to go ahead and just do the rest of this page together, how many waves are shown? We're going to count the waves. I see that I start at a trough, so I'm just going to count how many troughs I see. So I see there's one full wave, there's two waves, here's a third, whoa, keep missing. Here's a fourth, and a fifth, and then a half. So I'm seeing 5.5 total waves here. And it's okay that you see half a wave on a graph. That is totally allowed. We just want to make sure that we are keeping that straight. We're going to use the height of the crest and the height of a trough to determine the amplitude. So we remember that the amplitude is the distance between your equilibrium point and your maximum or your minimum. So first thing I need to do here is I need to find what my equilibrium is. Well, I see that my maximum is at 0.4 and my minimum is at 0.25. So there's about a 0.15 difference. So if there's a 0.15 total difference here, my equilibrium point is going to be right in the middle, which is going to be 0.075. And that actually tells me half of that distance from max to min is also what tells me my amplitude, 0.075. And we're going to throw our units of meters on there. If you have a position time and position graph for the same wave, the amplitude on both graphs should be the same. Here we only have that position time graph though, so we can extract that information. Okay, so show how you can use the total number of waves in 5 seconds to find the period and the frequency of the wave. So we counted 5.5 total waves. So first thing I'm going to find is the frequency, because I just know that's number of waves divided by time. And I have 5.5 waves in 5 seconds. So if I go ahead and throw that in my calculator, I end up with 1.1 hertz. Okay. And then our relationship between period and frequency is actually quite nice. I'm going to add this to my notes on the other page, so I would add this back to your green page. So your period is actually equal to 1 over your frequency. So they're essentially inverses of each other. And so that's also true that your frequency is equal to 1 over your period. So if you have one, you find the other. As your period gets larger, your frequency gets smaller, and vice versa. And that's just a feature of this relationship here. So if I go back here, I know what my frequency is, so I can go ahead and use that to find my period. Period is 1 over frequency, so 1 divided by 1.1, which gives me 0.91, about 0.91 seconds. And we could go ahead and take a look at that. It looks like my wave ends right about there at that 0.9 seconds. So that's kind of how we find our period and frequency and how we find that from our graphs. So go ahead and continue on, complete the rest of page 10 and page 11, and write down any questions that you have somewhere on your paper so that we can go over them in class. Thanks, guys.